We now come to section 4, which is going to be talking about formal charge, and I'm hoping actually to get into section 5 as well because they kind of go hand in hand. So section 4 talks about formal charge. What is formal charge? Formal charge is another way to determine the best structure of a Lewis dot diagram. It's a way to track where the electrons are in a particular drawing. When I ask you to draw formal charges, what I'm asking you to do is to calculate what is the charge for every single atom in a molecule. Now that sounds like a lot of work, but it's actually quite simple. The actual definition or equation to solve formal charge is you would look at the atom in question and ask yourself what's the number of valence electrons, and then subtract from it what's the number of associated electrons. Now you might be asking, what does that mean? What does the associated electrons mean? Well, I'll show you when I take a look at some examples, but that's the formula to calculate formal charge for every single atom. And as we go through some examples, you're going to see how there are some common trends that are going to help us out. Alright, so let's take a look at some examples. In example 4, we're looking at 3 particular substances. Let's first look at ozone. I'm going to draw this pretty quickly so that way we don't have to waste a lot of time with it, because by now hopefully you're feeling better with Lewis dots. So ozone is just simply 3 oxygen atoms bonded together. So oxygen has 6 valence electrons, 3 oxygens means we have 18 total. And if we draw our 2 single bonds there, okay, we have 14, 2, 4, 6, 8, 10, 12. We have 2 left over. We're going to stick them right there. And we're going to pull that lone pair over there to create our valid Lewis dot structure. Now, yes, there is resonance. Okay, there's another way I could have drawn this. I could have equally drawn it, and let me actually do that. I could have equally have done the double bond on the right side. And I'm actually going to do that so you can see that there is resonance here, right? There's a resonance structure. There's a different way to draw it, so I need to do that. I need to separate it with a double-headed arrow. Okay, but nevertheless, that's ozone, right? What I want to do is I want to calculate what is the formal charge for every single atom. So there's 6 oxygen atoms between these 2 drawings, right? So because you have to do it for both drawings. What's the formal charge? Okay, so here's how you do it. Let's take a look at this oxygen right here. First of all, how many valence electrons does oxygen have? It has 6. Minus, how many associated electrons does this oxygen have? So what do I mean by that? Well, associated means how many electrons are assigned to that particular oxygen. So we have 1, 2, 3, 4, and then think about here. You have 2 electrons here and 2 electrons here. So there's 4 electrons here, right? Well, you can think of it, of these 4 electrons, this oxygen owns half of those 4 electrons. So it owns 2 of the 4. So 1, 2, 3, 4, and then 5, 6. So there are 6 associated electrons to this particular oxygen. Now there is another easier way to think about it. It's a shortcut. Okay, it's not scientific, but it's going to be a shortcut for you. I tell my students, just look at how many things are touching the oxygen. There are 4 dots and 2 lines, 6 things. So that's how many associated electrons there are. So 6 minus 6 equals 0. So what does that mean? That means this oxygen has a 0 formal charge. So how do we show that? We don't do anything because it has a 0 formal charge. All right, let's do the same thing for this central oxygen. Oxygen has 6 valence electrons minus how many associated electrons does this oxygen have? Well, how many things are touching it? 3 lines and 2 dots. There are 5 things touching that oxygen, so there's 5 associated electrons. 6 minus 5 is positive 1. So what that means is this oxygen right here is going to have a positive 1 formal charge. Notice what I do. On the oxygen, I put a positive sign and a circle around it. I don't have to write the number if it's just 1. So if it's plus 1 or minus 1, I don't have to put the number. Just the positive is fine. What about this oxygen over here? How many what's the formal charge for this oxygen? There's 6 valence electrons minus, how many things are touching this oxygen? Well, there's 6 dots. I know those 2 dots kind of ran together, but there's 6 dots plus 1 line. There are 7 things touching that oxygen. So there's 7 associated electrons, meaning it has a -1 formal charge, and that's how I would draw it on that oxygen. If you did formal charges correctly, when you add them all up, it should give you the total charge for that particular molecule. 0 plus +1 plus -1 all cancels out to be 0, which, notice O3 is a neutral compound. It should all equal 0. You also need to do formal charges over here as well, but it should be easy because you know how everything's bonded. So the oxygen in the middle is still going to be +1. The oxygen that's singly bonded is the -1. And the oxygen that's doubly bonded is the one that's 0. So I don't have to redo the math. Now, a couple things before we move on to the next one. First of all, some common trends. Oxygen is one of the most common elements. You will see it all the time. So this is important to note. When oxygen is singly bonded in the terminal position, it will have a formal charge of -1. Notice that was the case right here, and also right here. When oxygen is doubly bonded in the terminal position, its formal charge will be 0. You don't have to put anything. Notice that was the case here and here. If you can remember those 2 tricks, that's going to help save you a lot of time. Okay, so let's go ahead and take a look at nitrate. So to save us some time, I went ahead and drew in the Lewis dot diagram for the nitrate ion. So it would be a good idea to pause the video now and get that written in before we move on. Notice for the drawings that there are 3 because there are 3 resonance structures, so I have to draw all 3, and they are ions, so I have to have the brackets as well as the charge on the outside. But we are concerned now with drawing in the formal charges. So you could do the math and figure out what the formal charge is for everything, or you can remember the trick that I taught you up here, because like I said, oxygen will pop up the most. When you see oxygen in the terminal position, singly bonded, it is going to have a -1 formal charge. So immediately I'm going to come down here. Notice oxygens are in the terminal positions. So when it's singly bonded, -1, -1, -1, -1, -1 there, and then -1 there. When oxygen is doubly bonded in the terminal position, it has a 0 formal charge. So I don't have to draw a formal charge here, here, or here because it's going to be 0. So the only element we have left is the nitrogen. So let's figure out what that would be. Nitrogen has 5 valence electrons minus, how many things are touching nitrogen? There are 4 lines, 0 dots. So -4, that's +1. So nitrogen is going to have a +1 formal charge there, which means also there, and also here, because the central atom's formal charge never changes. To make sure I did this right, let's add up all my formal charges. What happens when I add -1, -1, and +1? I end up getting -1, which, oh, look at that. That is the charge of the ion. So I know I did that correctly. All right, let's do one more together. Let's do fulminate. Alright, so once again, to save us some time, I went ahead and drew in the Lewis dot structures for fulminate. Notice for fulminate, I had to tell you that nitrogen is the central atom, because if you were to just look at this, based on what we've done so far in this topic, you would have assumed, rightly so, that carbon would be the central atom. But fulminates are actually different types of ions, and so I had to specify for you, and I'll do that. I'll specify that in those cases what the central atom is. But fulminates are actually extremely unstable. They're extremely explosive, and we're going to explain to you in this video why that is. So I have the Lewis dot structure, and notice there is resonance. This is very similar to the OCN -1 that we saw in a previous video, but it's slightly different, and you're going to see why that is. But what we want to do is we want to determine what the formal charges are going to be. So first thing I'm going to do is I'm going to go through and say, okay, oxygen that's singly bonded is going to be -1. Oxygen that's doubly bonded is going to be 0. And oxygen that's triply bonded, we could do the math just to, double check. Oxygen has 6 valence electrons, minus there are 5 things touching it, so oxygen would be plus. But you might have remembered that from when we did ozone earlier. All right, next thing I would do is let's figure out the formal charge for nitrogen. So nitrogen is 5 valence electrons minus 4 things touching it. So it's a +1 formal charge there. And since nitrogen's the central atom, it will be +1 for all 3 of those. I don't have to redo that math because it's going to be the same. All right, now we just have to figure out carbon. So carbon is 4 valence electrons minus, in this first drawing there are 5 things touching it, so that's going to be -1. And if I take a look at my 3 charges here, negative and positive would cancel out, leaving the negative left over, which is the charge for the whole ion, so I know I did that correctly. If I take a look at carbon in this second one, 4 valence electrons minus there are 6 things touching this carbon. This time it's going to be -2. That's the first time we've actually seen a formal charge that's not of magnitude of 1. And then finally, this carbon up here, 4 valence electrons minus 7 things touching it. This carbon's a -3. All right, so that would be the formal charges. And I didn't check this for the second and third one, but let's see. -2 plus a +1, that's still going to give me negative. And -3 plus 2 positives is also going to give me my -1. So I know I did those correctly. Now, what the heck do all these formal charges tell you? Formal charges are going to help us figure out the best, or most stable, I should say, most stable structure. So one thing to keep in mind, that Lewis structures where all the formal charges are 0 is preferred. If you can get the Lewis dot structures bonded in such a way where they're all 0, that is to be preferred. Now, if you're looking at an ion, for example, the nitrate ion, there's no way you could get everything to be 0 because you know something has to be -1. So in that case, small formal charges like plus or minus 1 or even 0, obviously, are much more preferred than plus or minus 2 or plus or minus 3. The higher the magnitude, the more unstable. And then finally, and this rule often gets forgotten, but it's very important, the best arrangements are where the more electronegative atoms have the more negative formal charge. So if we were to take a look at that OCN molecule that we did in a previous video, I have those Lewis dot structures here. Notice that, this first one has a -2 formal charge. That's not the most stable. Now, if I take a look at the second and the third, well, we have a -1 here and we have a -1 here. Those both seem pretty plausible, but one of these drawings is more stable than the other. How do I know? Well, it's either nitrogen has the -1 or oxygen has the -1. Which one of those two elements should be the negative formal charge? The more electronegative element should be the more negative formal charge. Out of nitrogen and oxygen, which one's more electronegative? Oxygen. And therefore, oxygen should be the one that has the -1. So the most stable, even though all structures do exist, the most stable is this one. It's the best structure. So if I go back to the previous screen, if I were to take a look at these 3 ions, first of all, which one is the most stable, would you guess? If you said the first one, that would be correct because the formal charges are low. But also, why are fulminates so explosive? Well, out of carbon, nitrogen, and oxygen, which element is the least electronegative? The answer is carbon. Carbon is the least electronegative. And do you see that no matter how we drew it, carbon always had a negative formal charge? That shouldn't be. Carbon should not have a negative formal charge, but there's no way around it. There's no way to draw a fulminate with carbon not being negative. And that's what makes fulminates actually extremely explosive, because they're very unstable ions to begin with. All right, we didn't get to section 5 in this video, but that's fine. We'll see you in the next video, and all of this is going to start to come together in the final video for topic 6.